Hi, I'm Ishani Carmichael, and I'm applying for the Mathematics PhD program at the Courant Institute at NYU. I'm currently a senior at Caltech, where I'm majoring in applied and computational mathematics with a minor in computer science. It's difficult to pick just one favorite topic or theorem in mathematics, but ultimately I decided to talk about the Perron-Frobenius theorem. Let A be a real square matrix. Suppose that A is also non-negative, meaning that all of its entries are greater than or equal to 0, and that A is primitive, meaning that we can find some positive integer k such that the kth power of A is positive. Here, by positive matrix, we mean that all the entries of A are greater than 0. Next, we let rho of A denote the spectral radius of A. The Perron-Frobenius theorem guarantees that rho of A is an eigenvalue of A, with algebraic and geometric multiplicity of 1. Moreover, the left and right eigenvectors of A corresponding to the eigenvalue rho of A have positive entries. Finally, the theorem guarantees that for any other eigenvalue lambda of A, lambda is strictly less than rho of A in absolute value. Now, if the non-negative matrix A is no longer primitive but is only irreducible, meaning that for each pair I and j we can find a k sub ij such that the k sub ijth power of A has a positive ijth entry, then we still have 1 and 2, but the strict inequality in 3 no longer holds. This theorem is fairly simple to state, but it's interesting from many perspectives. For instance, the Perron-Frobenius theorem has been proved several different ways, using a probabilistic proof, using Brouwer's fixed-point theorem, or using an argument based on a min-max functional, among likely others. When we consider all the variants of this theorem, including those specific to positive matrices and stochastic matrices, the Perron-Frobenius theorem has many interesting uses. For example, it tells us that if we have an irreducible and aperiodic Markov chain Xn on a finite state space with stochastic transition matrix P and invariant distribution π, then the distribution of Xn converges to π as n goes to infinity. This theorem can also be useful for studying epidemiology or demographics. For example, suppose we use a deterministic model for the distribution of the size of different age groups in a population that evolves according to some transition matrix. Then, knowing the maximal eigenvalue guaranteed by the Perron-Frobenius theorem, and whether this eigenvalue is greater than or less than 1, can help us to understand whether there are certain initializations that cause the population to grow unbounded or to collapse to 0 under the model. And of course, a very famous application of the Perron-Frobenius theorem is in deriving the Google PageRank algorithm. Next, I'd like to tell you why I want to obtain a PhD in mathematics. I'll start with the obvious reason. I love math, and after my undergraduate studies, there's so much more I want to learn about the field. It's fascinating that we can use mathematics to obtain such diverse results, ranging from these concise and concrete formulas to more abstract concepts in analysis or mathematical logic. I want to learn more about how to study properties of mathematical structures and solutions of complex problems. In addition, I'm fascinated by the study of numerical algorithms and approximations, and I would like to learn more about how we can design numerically stable, computationally efficient, and accurate methods of approximating solutions to various problems, especially when an exact solution is difficult to find. I'm also excited to learn more about the intersection of mathematics and data science, and how mathematics can be used to analyze performance of data science methods. I also hope to gain a better understanding of how to mathematically model phenomena that arise in applications, for example, for fluid dynamics, computational medicine, or atmospheric sciences, just to name a few. And ultimately, I hope that earning a PhD would be the first step to eventually pursue a research career. Lastly, I'd like to explain why I'm applying to Courant. Of course, Courant is a leader in mathematics research, and this program particularly appeals to me because it marries so many aspects of mathematics. Because Courant houses both applied and pure mathematics and is closely affiliated to the computer science department, I think I'd have the flexibility to learn about many different topics. Something else that really appeals to me about Courant is that after speaking with current students and alumni, I've learned that the institute has a collaborative environment. At a place like Courant, I would have so much to learn not only from faculty but also from my peers, so I'd love to be in a place that encourages a collaborative approach to research and learning. Thanks for watching, and thank you for your consideration.